Test point A, you got -4, right?
Yep, -4 volts. And that would be like me measuring across my source, right?
Yep.
So I have my red lead on my negative side, right? So that's going to be inverted, right? Because I got a positive lead on my negative side of my power supply, right? If I were to do this, then I'd create a positive voltage. But my leads are actually, my red lead's on the more negative, my black lead's on the more positive, so that's going to give me a negative voltage.
I'm just getting screwed up there. Because I'm thinking you go across and every time you see a minus, you minus go up.
Nope, yeah, it's always algebraically added.
You don't start from -4, you start with 0. So when you're starting at
Yeah.
you start with 0.
Oh,
and then
that's
you
right.
start
I'm
with
screwed up.
Yeah, yep. Yeah, so you always add, and you're just adding all your negative numbers as you going down. Does that make sense?
Started with -4.
Oh yeah, don't start with -4. Even though we already knew it was a -4, just by knowing what we know, yeah, you still would start out with 0. Yeah. All right, so what do we get for our voltage drop across R1?
4.314 volts peak to peak.
4.341 volts peak.
314.
All right, and then R2? 1.216 volts peak to peak. Good. Using your units?
9.2. 9.216.
9.216 volts peak to peak. All right. All right, and then my R3?
6.471 volts peak to peak.
Good. All right. So then, what am I going to measure at test point A then?
20 volts peak to peak.
20 volts peak to peak. No polarities now when we're doing the AC. Okay, and then for test point B?
15.69 volts peak to peak.
Okay, and then test point C?
6.471.
471 volts peak to peak. And then test point D?
Plus or minus zeros.
Yeah, no polarities on the AC because it's switching back and forth. So we just go to the polarities on that one. That one we can use actually just the zeros. Yeah, so this one's always going to require polarities. But test point A for AC, that's not going to require any polarities because it's switching back and forth. All right. So now our next step is now we're going to be kind of analyzing and taking a look at it. So if we were putting it on the oscilloscope, what would we get at each test point? So if we were to rough sketch this out, I'd have an AC signal coming off of test point A. My AC signal is going to be at 20 volts peak to peak. That means I'm going to be going up to a positive 10 volts peak down to a negative 10 volts peak. But since I'm superimposing it onto a DC power supply, my DC reference is going to be located right here. My DC reference now is going to be at -4 volts DC. So that means that I'm going to have 10 volts above it and then 10 volts below it. And then that's how we're going to calculate out what our Vmax and our Vmin is. And I know that my AC signal is always going to be right on my DC reference. So if I know that I'm at my -4 volts, and I'm going to be 10 volts above it, what's my value of my peak here?
Plus 6 volts.
Plus 6 volts. That's going to be considered my Vmax. Okay? Then what is going to be my Vmin if I know that I have 10 volts below it?
Minus 14.
Minus 14. That's going to be my V min. So my potential difference between my V max and my V min is going to equal what?
20 volts.
My 20 volts. Then you know that you did that right. So that AC signal, if I were to put it on the oscilloscope, is going to be right on that negative 4 volts DC. My maximum is only going to go up to the positive 6 volts max. And then my V min is going to be going down to my negative 14 V min. So my V max is going to be positive 6 volts. And the units is V max. And then I'm going to go down to a negative 14 volts V min. And those also require polarities.
How did you get the negative 14?
Okay? Yeah, so we know that we're going to be 10 volts below that negative 4 volts, right? So if I just take a negative 4 volts and subtract another 10 volts to it, I'm going to get a negative 14. I'm just bringing it down on my number line, I'm just bringing it down. So that the difference between it from here to here is going to be 10 volts. Half my voltage peak to peak. So my potential difference right here between negative 4 and negative 14 is going to be my 10 volts. Okay? But that AC signal is going to be right on that DC reference. And we do this, in this case, we do this a lot, especially when we get into our amplifiers and stuff like that, and get into our solid state components, especially for transistors, because our solid state devices are going to have polarities and they only conduct with current flowing in one way. So a lot of times what we're doing is we've got an AC signal that's going both positive and negative, and then we superimpose a DC power supply and bring that whole AC signal up that is always going positive. So that way my transistors or my other amplifiers are always going to be conducting. So we do this a lot. We're constantly superimposing a DC voltage onto our AC signal to bring that whole thing up, to shift it either all the way up or shift it all the way down, so that it's either always going positive or always going negative. All right, then on my test point B, then what's my DC reference going to be? Yeah, negative 3.137 volts DC. And my AC signal is going to be riding on that. Okay. So how much voltage am I going to be riding above my 3.13 volts DC? Oh, 317.
No, I got plus 4.
Okay, so what's my voltage peak?
7.845 volts.
7.845
845.
volts. Okay, so basically it's just half of my voltage peak to peak. So then all I'm going to do is I'm going to take a negative 3.137 volts and add 7.845 volts peak to get my V max. And what did you say you got?
4.708
volts, and that's going to be my V max. Now I'm going to just take the same number, and I'm just going to subtract it from my 3.137 volts, and I go to, what do I get for my V min then?
Negative 10.98 volts.
That's my V min. Okay? So my V max is going to be 4.708 max. That's positive, and then I'm going to go down to a negative 10.98 volts V min. Okay? All right, everyone following along so far? So it's always writing on that DC reference. And then again, here's where we got to do, sometimes we have to do our conversions. We have to calculate out what is our voltage peak, and add it to our DC offset, or our DC reference, and then subtract it from our DC reference to get our V min. Alright, so then what's my DC reference on test point C going to be then? Negative 1.294 volts DC. So that's going to be my DC reference. And then my signal is going to be right on that. So what's my Vmax going to be equal to then?
Positive 1.942 volts. 42.
Max. Alright. And then my V min is going to equal to what?
Negative 4.530 volts.
543?
30.
Say it one more time.
4.530.
530.
$4.530, did I get that right?
Yep.
Alright. And so that's going to be my V min. So I'm going to have my V max is going to be a positive 1.942 V max. And my V min is going to be a negative 4.530 V min. And then always double check your work. You know, there's always a way of double checking your work. If I take what the difference is between these two numbers, it always equals my volts peak to peak. Then you know I did it right. Okay, so then on test point D, then what's my DC reference going to be?
0.
0 volts DC. And then what's my, so now my AC signal, I don't really have an AC signal, that's all at 0. So basically it's going to be a flat line. So my V min then, or my V max then, is going to be plus or minus 0 volts, and my V min is plus or minus 0 volts. It's just going to be a flat line. It's just my point of reference. It's just my ground. And when you're graphing, a lot of people like to, when they're graphing this stuff out, what they like to do is they like to put in that line, that DC reference line. They like to draw that line all the way across there so they can see where they're drawing their. Avoid doing that. That's not the proper way of doing that. If you draw that line in there on your graphs, just to represent where your DC reference is, it's actually indicating that that's a signal that you're measuring, because we can measure multiple signals on our oscilloscopes. We can have multiple channels measuring on our oscilloscope. And if somebody sees that, they're going to think that that's part of the signal. So make sure you avoid trying to draw that line in there. Anything you draw on that right-hand side of this, of your numbers, is going to be assumed that's what you're seeing on your oscilloscope. Okay? And so, you know, and then when we're always kind of graphing, we're also kind of taking a look at the 5 things that we need to know about a waveform. Those are on that top of that one cheat sheet here that I gave you. You're looking for what the wave shape is. Well, we drew up our sine wave. We gave it our amplitude. We did it as V max and V min. Time, we didn't know what the time was because I never gave you any frequency, so we can't do any time on that. We got our DC reference on there, and then our phase. And then our phase would be, we're just assuming that it would be at 0 degrees. We're just starting them all at 0 degrees. There is no phase shifts or anything like that on this particular one here. All right. So again, this is what we measure on our oscilloscope. And we'll jump ahead a little bit and we'll talk about our oscilloscope since we have this circuit in here, because then we can show you how how you would measure using the oscilloscope. So when we're talking about using the oscilloscope, you know, we have the real one that's on here. You're going to have, these are 2 channels, so there's going to be 2 probes on here. So you're going to have the probe that actually is going to clip onto your test point. And remember, don't clip on your components, but clip on a test point. You know, bring out a jumper out of your board, clip your probe onto there, and then you're going to have a ground clip on there. And that ground clip is always going to be connected to your point of reference, your ground. That one, again, just like when we're doing test points, this ground clip can never move. And that's actually physically grounded to earth ground.
It's not just a point of reference here.
Yeah, it's a point of reference. But when we hook up that ground clip from our probe and we tie it right to here, we're physically then going to actually tie this right to our earth ground. It would be just like going to your ground plug on your thing. It's really actually physically tying it right down to earth ground. It can be a floating ground while the circuit's just sitting there, but the minute I clip that ground clip on there, I just tie this point of reference right to the earth ground. Otherwise, normally it's just a point of reference for us. It's not an earth ground or anything like that. It's just a point of reference for us. But when I put that ground clip on there, I am physically tying it onto my ground clip. So what you want to do is then you're going to have your ground clip clipped onto there. Your probe is going to put your channel 1 on channel A there. Then that ground clip, that's going to come down. And we can clip it right on to test point B there. And then I'll bring up the screen about the things. So that's how you're going to hook it up. If I want to try measuring the voltage drop across just R1, you know, like on our probe when we're using our digital multimeter, if I'm using just a digital multimeter and I'm only running at something less than 1,000 hertz, you know, I can put a digital multimeter on here and put it across test points A and B, and I measure the voltage drop across R1. If I did put my digital multimeter on there and I measure the AC voltage going across it, what type of voltage would I be measuring using my digital multimeter? What type of units?
RMS.
RMS, okay? So you wouldn't measure the 4.314 volts peak to peak, you'd measure the RMS value of that. So you'd have to divide this by half and then multiply it by 0.707, and that's the voltage that you'd be measuring with a DMM. My oscilloscope is actually going to be measuring my volts peak to peak, or my peak, whatever I'm looking at, or my Vmax. I can have a whole bunch of different things on there. So one thing that people like to do is if all of a sudden in lab they tell you to measure the voltage drop across R1, what people will do is they'll kind of treat it as a DMM. They'll take their ground clip and they'll put it across test point A, and they'll measure their voltage. And when they measure their voltage on their oscilloscope, what they're going to actually end up measuring is our 20 volts peak to peak with a -4 volts DC offset. You're not going to measure your 4.314 volts peak to peak. Anyone know why? Why would I measure my source voltage going across R1 if I move my ground clip up to test point B? Well, I said that this black lead, that's my ground clip, right? That's my point of reference. So what happens is I put my point of reference on there. Now, just like we did in our troubleshooting, what just happened was I just shorted out test point B to D. I have a short going all the way across there, because if this is tied to earth ground and this is earth ground, that's just like me shorting out R2 and R3. I have a direct short going across there. So that's why we can never, what we call, you can never float the ground. That ground can never be floated. So always make sure that that ground clip is always staying on your point of reference. So I'm going to bring it down here and tie it onto my ground. So whenever what we call float the ground, you'll hear me calling that, you'll hear me hollering that out in the lab, I'll say, oh, don't float the ground. If we're working with something with high voltage and high current capabilities, and we go ahead and float that ground, that current is actually physically going right through the oscilloscope and then right back into the earth ground. So if we're measuring something with very high voltage, with a lot of current capabilities, that wire on this ground wire will actually burn right off. Or your oscilloscope is going to burn up. Okay? So you're going to have to be very careful about floating the grounds when you're out in the industry.
That's all right. Oscilloscopes are really cheap.
Yeah. Another problem that can exist too is if we're so we'll put our channel 1 here. If I put my channel 1 there and I float my, and I end up floating my ground, and I bring my ground lead, let's see, we'll say we'll just bring my ground lead over to test point C. Now what just happened was I just shorted out R3. So now all that voltage that was going across R3 is now shorted out. All this voltage here, the 6.471 volts peak to peak, has to go divide up against these other two resistors. So those resistors, the voltage are going to increase on that. The current's going to start to increase. And then my power is going to start to increase. And then if my power increases and my components can't handle that power, I'm going to end up burning out my components on my circuit board. And people have destroyed $1,000 boards just by floating the ground and shorting out that circuitry on their board and burning out components on that circuitry. So you always have to make sure you know where your point of reference is when you're locating your ground on your probe there. All right, so if I want to, what I want to do is if I want to measure a voltage drop across R1, what I want to do is I want to hook up my probe lead, channel 1, and that's going to go off to my oscilloscope. My ground clip is going to go down to my ground. And then what I'm going to do then is I'm going to also hook up another channel. And I'm going to hook up channel 1. Or channel 2, I'm sorry. I'm going to hook up channel 2 up to probe B. Now once I take one ground clip from either one of my probes, it doesn't matter which one it is, but once I hook up a ground clip onto it, the other channel doesn't need to be grounded necessarily unless you're really working with some high frequencies or something like that and you really got to watch out for noise. But even on our circuits, you know, typically if I just ground it out once, I'm good for the whole circuit. I don't have to ground out all the probes, I just only have to ground out one of the two probes. Unless I'm working with some real high frequencies or something real noisy. So what I'm going to do is I'm going to measure the voltage drop across R1 is what we have on our oscilloscopes. It's a math function. And you're going to want to use that math function on there because we do this a lot because if we want to find out what the voltage drop across R1 is, then you're going to measure the voltage across R1 and take the difference of channel 2 from it. So all I'm going to do is I'm going to take channel 1, subtract channel 2 from it. That's going to be my, so for example, if I'm measuring my AC voltage here, I have channel 1 is going to read my 20 volts peak to peak, and my channel 2 is going to read my 15.69 volts. If I take my 20 volts and minus my 15.69 volts, what do I get for voltage? I'm going to get my 4.314 volts. Okay? So that's a math function that we use. That's how we calculate all our voltage drops across there. We need to use two channels on there. And I'll bring up our picture of our oscilloscope and show you how all that works because there's a lot more to hooking up an oscilloscope. Now with a MIGAX, everything I just talked about can be thrown out. MIDAX does a different type of measurement. It does a differential type measurement. On the MIDAX, internally, there's going to be an op amp. So this op amp is inside the MIDAX. And there's going to be two pins coming out of it. It's going to be an inverting pin, what we call an inverting pin, and a non-inverting pin. This one here is going to be my AI 0 minus, and then this other one is going to be my AI 0 plus. And what it does is it does a differential type measurement. There is no point of reference, there's no grounds or anything like that. So everything internally here is all floating ground already. So what I can do with my MIDAX, if I wanted to measure my voltage across R1, is I can actually, so I would want to put my AI 0 plus on test point A and put my AI 0 minus on B. And what it's going to do is it's going to automatically take the differential of these two voltages. It's going to see that I have my 20 volts at test point A, and it's going to see that I'm going to get a 15.69 volts, and it's going to know that if I take the difference between those two numbers, it's automatically on my oscilloscope is going to give me my 4.2 on 4 volts. So on this particular one, we can actually float the ground. The A ground on your circuit is still going to be hooked up. Your A ground is still going to be, when you're hooking up to MIDAX, coming out of your function generator. Function generator is going to be coming out of my A0 or my AO channel 0. And then it's going to hook up to A ground. Your DC power supply, that one can be hooked up to A0 channel 1. See here, I want to make sure I'm saying that right here. I think that might have to think about that. Let me think about that one here. 01. Yeah, that would be correct. And then internally, let's see here. I gotta think about that here. Yeah. That would be that. Let me think about that one here. I gotta. Wait. I gotta think about that. I gotta think about how to wire that up with my DAC using with the function generator. We've always done it with the actual function generator. So I gotta think twice about that one. We'll come back to that. I'll think about that at a break here. But anyways, for the oscilloscope though, you're gonna be taking your AI 0 plus and your AI 0 minus. If you want to do it like the oscilloscope would be, and just use your A0 minus and tie that to your point of reference, then that's how you would use it for. Then I could just go ahead and bring my A0 plus, bring it to test point A, I'd measure my 20 volts peak to peak, bring it down to test point B, I'd measure my 15.969 volts peak to peak, and so on the way down. So there's two different methods that you're going to be working with when you're trying to analyze your circuits for the first time. So I do recommend you using both the oscilloscope and also the real function generator. And I'll take a look. I got to think about this one here about wiring up the MIDAC. We've never tried it before. I got to think through that one. All right. So any questions so far? Really? All right. Yeah, so looking up all this stuff gets to be a little confusing there. So when we're using the MIDAC, it's okay to float to ground. You can go ahead and go right across your component, but with the oscilloscope you can't. All right, let's while we're talking about the oscilloscopes, then let's dig a little bit more into the oscilloscopes here. All right, so I handed out a little sheet, and all oscilloscopes. This one's very similar to the Textronics one that we have in class, but all oscilloscopes work about the same way. Let's take a look at that. Let's open that up here. You also might want to have your saturated oscilloscope reading ones out there too. We'll kind of use that as a kind of start looking at that one too. All right, when we're in there. Oh, let me keep you up. Just kick his chair.
Hey, you quiet over there.
Tom used to have a squirt gun. Still has that. Jed, the guy that I replaced, I don't know if you ever seen it, the big mallet that's in the other room there. He has a big sledgehammer. Man, we can bang that on the table every 10 minutes. When he's seen somebody's head bobbing.
Get your inspiration on that chick thing on the road and smack her next to their head.
All right, so there's three major parts to the oscilloscope. We're going to have our so there's three major controls on an oscilloscope. We have the horizontal position, we have the vertical position, and then we have the trigger. We have to kind of work with all three of those all at the same time. So our horizontal position, that's going to indicate it's going to be everything going off this way. This is going to be based off of our time. So our horizontal position is our time. Okay? So if we have a certain frequency, we have to make sure that we allow enough time so that we can at least display. So when we're graphing, we always graph out 2 complete cycles. But when we're doing measurements on our oscilloscope, what we like to do is we like to have it so that when I adjust my time, I'm going to just use an AC signal here. I want to have 1 complete cycle on there. Now, So one complete cycle might not get to all 10 divisions. It might only come up to 8 divisions. So what I want to do is I want to adjust my seconds per division. That's this knob here. I'm going to adjust my seconds per division so that I accommodate enough time so that I just display one complete cycle. And so I'm going to adjust that certain time, and we're going to take a look at how you calculate all that out and stuff like that. But that's going to be the one that adjusts our time. You know, so for example, if this thing was taking 16 milliseconds, let's say it's a 60 hertz signal coming from our wall outlet, and it's 16.67 milliseconds it takes for it to complete one cycle, what I'm going to want to do is that my screen is going to be broken up into 10 divisions. So what I want to do is I want to make sure that I have at least 16.67 milliseconds going over my whole 10 divisions. So that means that, just because I know what the divisions are on the oscilloscope, I know then that I would want to set my horizontal position and my seconds per division to 2 milliseconds per division. I know that is one of my divisions on there that I can either do on the analog scopes or the digital scopes. I think on the digital ones, I think it might be 2.5 milliseconds. And on the analog, I think they have the 2 milliseconds, but we'll just keep it for simplicity, we'll just keep it as the 2 milliseconds per division. So what that means is that for every division, it's going to be 2 milliseconds. So over 10 divisions, I'm going to show a total of 20 milliseconds over my whole 10 divisions. Okay? So then I know that my 16.67 milliseconds that I want to show is going to fit on my screen. It's not going to be quite going to the all 10 divisions, but it'll get, approximately to about 8 of them. Just a little over 8 divisions and stuff. And that's going to give me my one complete cycle on there. Now I want to do that for the reason that, so that when I'm measuring this stuff, the higher the resolution I have, the bigger this my signal is, the easier it is for me to measure my divisions. Okay? So that's going to be my time, and I want to make sure I got one complete cycle going across the whole entire screen. And I'm going to do that with my seconds per division. My other one then is my vertical position, and this is going to be my voltage. And that was going to have my divisions of volts per division. That's going to increase the amplitude of this. Okay? So let's say we'll keep our 20 volts peak to peak. If I want to have 20 volts peak to peak, then I know that I want to set my units per division to 2 volts per division. So I'm going to just turn my dial, and then on the bottom, over in the corner here, it's going to say how many volts per division is. And I'm going to set that for 2 volts per division. Then I know that my full scale then, over all 10 divisions, I'll be able to measure my 20 volts peak to peak. Because I got 2 volts per division. And so then my amplitude of this thing is going to be as large as it can. And that's going to be my vertical position. That's my amplitude. The third one is our trigger. This is where people get kind of confused on setting up their trigger. Their trigger is telling it, because since this is a graphical representation of the sine wave, of what we're actually getting out on our test point, we have to tell the oscilloscope when to start to draw. And that's where I deal with my trigger. So, for example, so I'm going to have an AC signal here, and this is going to be continuing on. It's always going to be constantly oscillating. We'll say it's at 60 hertz or 16.67 milliseconds for our period. Well, that oscilloscope is going to need to know when to draw it. And so what it does is it does it based off of a level, off of a voltage level. And on the left-hand side, or on the right-hand side, you're going to have a little arrow on there. That's my trigger level. So typically what we want to do, depending on where our DC reference is, we'll just say that we have no DC reference line here and that my voltage DC is at 0 volts. What typically I like to do then is set up my trigger level to be set at 0 volts DC. Then one of the other options on it, if I click on the menu, then the menu will come up and it'll ask me what I want to do. You know, do I want to do it on a rise, or do I want to do it on a fall? So what it's going to look for, it's going to be that trigger is going to look for when it gets to 0 volts, and if my voltage is increasing. So if I have it set on a rise, which we typically use is on a rise, as that voltage starts to go past 0 and start to rise, it's going to start drawing that signal. And it's going to draw that signal all the way across until it comes back up to the beginning of the cycle here again. And then all of a sudden it's going to see another, so like for example here, it's going to cross 0 here again, but this time the voltage is on the downward side. So it's not going to redraw it again. It's not going to draw it at that point, but it crosses 0 again, and the voltage is increasing. So then it's going to start drawing again at that point. And every time that goes on a rise, crosses 0 and goes up on a rise, it's going to trigger the oscilloscope to start drawing. If I have my voltage trigger level set too high or too low, so for example, we'll say that this is at plus 10 volts, and it's going down to negative 10 volts. And I have my trigger level set at 11 volts. Say at plus 11 volts. Got my trigger set at 11 volts. What happens is that the oscilloscope doesn't know when to trigger. It doesn't even see the signal. The signal never passes that arrow there. It never sees that trigger. So what the oscilloscope does is just based on time, the oscilloscope itself has a little oscillator in it, and it's sitting there triggering the trigger all the time. And if that oscillator isn't set up to the correct time of what our signal is, what happens is that it just keeps on, every time that oscillator goes by, it just starts redrawing the sine wave again. And it just keeps on, and we don't never know when it's going to start to draw again. It's just going to kind of look like a whole bunch of oscillation. It's just going to look like a whole bunch of sine waves on there. So if you get something that's kind of oscillating and all these different waveforms on there, it's probably because it's not knowing when to start drawing your signal again. And you'll get a little garbled mesh on your screen that looks something like that. So all you need to do is you need to bring down your trigger level, get it down to 0 volts, do it on a rise, and tell that oscilloscope when to start drawing. And then that'll draw it in the right way. Another thing on the trigger is that we also have to tell which channel to trigger off of. For example, here's a 4-channel oscilloscope, and we have to tell which channel we're going to trigger on. And I think on the arrow, maybe not on the arrow, but in the trigger menu, it's going to ask for what you want to trigger off of. Either channel 1, channel 2, on ours, for either example, it's going to be either channel 1 or channel 2. What we want to do is, it depends on what our reference voltage is going to be. Now when we get into RC circuits, that's going to be very critical on making sure that we pick the right channel. Because we want to know which one is our reference voltage. So for example, on channel 1, we'll just say that we're going to set up our trigger level on channel 1, which is the most typical application that you're going to do is you're going to set up on channel 1. And if we had our circuit back up here and we went to test point A, we're going to measure our source voltage. So test point A is our source voltage. That's going to be our channel. So what would actually happen then was on channel 1, that's going to give me my trigger, and it's going to draw the source voltage. And it's going to start out at 0 volts, and it's going to do it on a rise, and this is going to be my channel 1. Then if we're doing like an RC circuit or an RL circuit, we might have another, you're going to see that we're going to end up having more than one sine wave in the same circuit. Nothing else, when we get into an RC or an RL circuit, our voltage and our current isn't going to be at the same phase. So what's going to happen is that we say, okay, well, I'm going to trigger at channel 1. That's going to be my 0 degrees. And then it's going to watch channel 2. If I have channel 2 hooked up to it, it's going to watch channel 2. And then when it sees channel 2, then it's going to automatically draw on channel 2 after that. But channel 1 is going to be our reference voltage. That's the one we're going to trigger off of. And that's going to be considered our 0 degrees. And then channel 2, when that one, it'll just start watching channel 2. Whenever it sees, after channel 1 triggers, it's just going to watch channel 2 and start drawing channel 2 in reference to channel 1. So the trigger, making sure that you select on the right channel for your trigger is going to be important. If, for example, if I don't have, let's say I don't even have a channel 2 going, let's say I don't even have that one hooked up, I have my channel 2 plugged, as my trigger mode, and all I have is channel 1 hooked up to my circuit, I'm going to get that oscillation again, because it never sees channel 2, so it's just going to start drawing channel 1 in random order again. So if you're getting that random order of a whole bunch of sine waves on your oscilloscope, it's either because of your trigger level or that channel, the channel wasn't selected correctly on your trigger. Okay? So not as easy as working with just a DMM where I can just hook it up, I can connect it anywhere, I don't have to make any adjustments, it has all the auto ranges and stuff like that. So it gets to be a little bit more complex hooking it up to it. Okay? And so whether if you're working with the MindAct or the real oscilloscope, they're both going to all have those same functions. It's going to have a horizontal position, a vertical position, and a trigger. All right, is any of that making sense? Follow along a little bit with it? Until you really actually dig into it, it's not, it's a little complex until we kind of dig into it. Let's see here. All right, so now we used to have digital and analog oscilloscopes, and we made use both of them. But since digital is kind of becoming the norm now, we can do so many things with the digital. The analogs still have their places, but boy, I tell you, the digital outweighs any of the functions that the analog does. One thing that we can do is, because it's all digital, it can store the image. So if it's if we just want to quick do a snapshot of it, we can save the image. We can even save it onto our flash drive and print it out on a printer. The math functions we have a lot more capabilities with our math function. So for example, if I want to do the math, so this is another function that you're going to use a lot. That's our math. That's what we're talking about, where you're going to take the difference between channel 1 and channel 2. But you can also multiply the two together. You can divide the two together. There's other math functions that you can do. Typically, the one that we're doing is we're going to be using the difference between the two and using the subtraction. We're just going to subtract channel 1, take channel 1 and subtract channel 2 from it. So get to know how to use the math function. Another one that's really a useful tool is our cursors. So as we kind of get through, as we get kind of past the basics of how to use a oscilloscope, then I'll start showing you how to use some of the cursors and stuff. But the cursors we can either do, I think it's lab 17 or something. Lab 17, they're going to have you measure the rise time and the fall time of a square wave. And that's where the cursors come in. Because nothing happens instantaneously, so for example, a square wave, we'll draw, Tom in digital is probably drawing nice little square waves that look like that. But in reality, if I spread it out over a amount of time, a square wave actually looks more like this. It doesn't go from 0 to 5 volts instantly. It takes a certain amount of time for it to get up there. And that's what we call our rise time and our fall time. And we can measure that with our cursors. So we can take our cursors and we can bring our cursors over and we can bring it over 10% above our baseline and 90% of our voltage. And we can take our cursor 1 and our cursor 2, and we can take the difference between those two and we can calculate out how much time that is it took for it to rise. This rise time is important when we're working with digital circuits because this is what we call propagation delay. Our circuits are going to see this delay, and if they're not going to trigger instantaneously, it's going to have to wait till it gets up to 50% of that voltage before it triggers our digital circuit. Well, we'll take a look at more of the pulse waves when we get rid of the oscilloscope here. But so cursors are very nice on these things. So get to know how to use the cursors. Make sure you know the 3 basic functions: vertical position, the horizontal position, and the trigger, and the match function. So those are the main functions that you really want to know how to use on a digital oscilloscope.